yesterday we have derived the solution for uniform plane wave with sinusoidal excitation. That is, the current source the variation of the current source is in the form of a sinusoidal signal, such as cosine signal. So let's quickly review important features of uniform plane wave with sinusoidal time variation. So the argument, as I already stressed out, as I already talked, should include both description for time and space and position. So it's in the form of omega t minus plus beta z. So the whole argument is sometimes abbreviated as phi for the function. And the time derivative of the argument phi is your angular frequency, omega, which is a multiple of frequency n 2 pi, the radian, the number of radian within one period. And if you take in the special derivative of the argument phi, you end up with beta, that is the phase constant, which stands for the number of signal within one unit length, say 1 meter. Okay, so the wavelength within 1 meter is the so-called phase constant, and it can be alternatively represented as 2 pi over lambda or omega over v. If you take in the partial derivative of the argument jointly, you can end up with the expression for phase velocity Vp, which is in the form of omega over beta. And of course, it can be replaced with a more general representation for the phase velocity, that is the product of frequency and wavelength f lambda, right? So the phase velocity Vp can be either represented with omega over beta or f times lambda. And as I already stated at the end of yesterday's lecture, I told you that Vp is in fact the so-called phase velocity. And the phase velocity can be different for the same wave, depends on which direction you are looking at. And the so-called 3 times 10 to the 8th, the velocity of speed, is actually the smallest, the lowest phase velocity of electromagnetic wave propagation in the space, all right, in the free space. If you looking sideways, if you're looking not the direction along the propagation, the actual propagation direction, you will end up with a higher phase velocity. However, unfortunately, the phase velocity doesn't carry out the information and energy. And if you looking at the propagation of energy and information, the things that you need to look at is, in fact, the so-called group velocity, which is always smaller than 3 times 10 to the 8th, right? Okay, and at the end of yesterday's lecture, we also have a quick look at the so-called frequency bands. The so-called microwave band is in the range of megahertz to 30 gigahertz. Above 30 gigahertz, the frequency band is referred to millimeter wave band. Millimeter wave band. And so here, here is a more clear definition. So the millimeter waves is 330 to 300 gigahertz, and microwave is 1 to 30 gigahertz. The most wireless communication standards that you are acquainted with, such as Wi-Fi or cellular phone, is in the range of a few gigahertz. All right, at this frequency band, the modern industry can produce components at a very low cost, relatively low cost in frequency smaller than 6 gigahertz. On the other hand, if you go to higher frequencies, you will the cost for the RF circuit. For the microwave circuit, it becomes quite substantial. It becomes more expensive. All right, and any questions about the frequency band? Well, okay. Unfortunately, the frequency band that is easy to use, that is cheap to fabricate, is crowded. It's already crowded. So nowadays, we are looking at a higher frequency, which is more challenging, technically challenging, not that cost-effective. However, because the lower band are already occupied, we need to go for a higher frequency. So, all right. So the academics already goes for millimeter wave, tetrahertz wave, something like that. But the commercial use is barely catching up mainly because of the cost. All right, and this slide tells you the definition for intrinsic impedance, which is even though the intrinsic impedance is labeled with the unit ohm, it's not a resistor. So don't be mistaken. It's not a resistance. It's just the ratio of electrical field over magnetic field. It happens to have units that is the same as ohm, as the resistance, but it's simply a ratio. All right, and the next thing we'd like to get into is power. We know what is the purpose, what is the usage or the purpose of an electromagnetic wave. Well, it delivers energy. The whole existence of our life, our civilization, is based on what? Based on the solar energy. Okay, so the sun delivers, well, from our own perspective, it's kind of an infinite amount of energy from the sun to the earth. All right, and so everything we build, everything we live on is originally based on the solar energy. And the solar energy comes in the form of what? In the form of electromagnetic wave, right? So in this part, we will try to discuss the association between electromagnetic wave and microwave power, all right? So the first thing you need to know is the cross product of electrical and magnetic field, right? So the product of E cross H is the so-called Poynting vector, 波应停向量。电场跟磁场的外积，你以前有听过吧？可能不是很熟了，但有听过吧？波应停向量嘛 ，Poynting vector， OK？ So the Poynting vector provides you the a representation of the energy propagating in the space. And in our previous discussion, in our previous lecture, we already derived the form of electric and magnetic field in terms of sinusoidal signal. Okay, so it's the electrical field is eta sub 0 over 2 times j sub s0 cosine omega t minus plus beta z, and the magnetic field has similar representation as the electrical field, except the magnitude is smaller. So here we only have one eta sub 0, that is the ratio of E field over H field. And here you have J sub S0 to the square, the square of the electrical field, electrical current density, and the square of the sinusoidal function. All right, the important thing about the expression here is the direction, because this is the result of a cross product. So we know that electrical field is in the which direction? In the negative x direction, and the H field, the magnetic field, is in either positive y direction or negative y direction. So the cross product is in the z direction. And here you see there's a positive sign and negative sign. So that stands for the propagating direction of the Pointing vector, the cross product of E and H field in the region of z greater than 0 and z smaller than 0, right? No. For z greater than 0, you have a positive sign for this pointing vector, and on the other hand, at the region smaller than 0, you have negative sign. So in this plot, you can see the green arrow. So that stands for the propagating direction of the pointing vector, or propagation direction of the field. And you can follow the right-hand squirrel's rule that the red arrow cross the blue one gets into the right-hand side, the green one. And on the other side, red cross blue give you the propagating direction to the minus z direction, the other green arrow, all right? So the product, the cross product of E and H field not only give you the direction of a wave propagation, it also give you the magnitude. So the magnitude is proportional to this product. And here's an example. So let's use this example 3.11, to review some important properties of electrical field in sinusoidal form, in sinusoidal format. So say we have an electrical field of this. Okay, so one important thing here is you see it has two components. It has S component as well as Y component, all right? And the two components have similar representation. You see the argument, omega t minus beta z part is the same for the two functions. However, one is a sinusoidal function, one is a sine function, and the other is cosine function. What is the difference between sine and cosine function? They are not that different, right? Sine and cosine function can be regarded as the same function with a phase difference, with only a phase difference of what, how much is the phase difference? 90 degrees, right? So say here, no. Do I have anything that is, nah, okay. Well, so sine and cosine is just only a 90-degree phase difference. Okay, so based on the argument, we can derive some important characteristic of this field. Okay, so like I already said, the argument is in the form of omega t minus beta z, omega t minus beta z. So using this form, you can identify what is omega. Well, omega t minus beta z, so omega is actually 3 pi times 10 to the 8th. Okay, that's your angular frequency. Beta z minus beta z, so what is beta value? It's pi, all right? So based on the knowledge of omega and beta, we can derive some follow-up important parameters, such as the frequency. Frequency can be found by dividing omega with 2 pi, so you have 1.5 times 10 to the 8th. So a more convenient way or more general way to describe the frequency here is what? 150 megahertz. 150 megahertz. Okay, 150 times 10 to the 6th. That is 10 to the 6th megahertz, right? So it's 1.5, 150 megahertz or 1.5 times 10 to the 8th, all right? And the wavelength, lambda, can be found from the phase constant beta. And from the definition, lambda equals 2 pi over beta. And we know from the previous page that beta is what? Is pi. Okay, so the wavelength is 2. And the corresponding velocity of phase velocity, phase velocity Vp is omega divided by beta. And it happens to be 3 times 10 to the 8th. That is the speed of light in free space. So we know that the author of this textbook is not making up some random numbers. Okay, so the number is consistent with the reality. All right. And you can also check up the number by taking the product of the wavelength and the frequency, lambda times f, which is also the same as 3 times 10 to the 8th, all right? And the description we have in the previous page says the electrical field has two components. One is vibrating in the x direction, and the other one is vibrating in the y direction, okay? And the next thing is to find the expression for its magnetic field. And this can be done by this, okay? We should know that for plane wave, one important properties for plane wave is the E field, H field, and the propagation direction is perpendicular to each other. So the E field, vector E, vector H, and the propagation direction, which I used to label it as K direction, are perpendicular to each other. And it follows the right-hand square's rule, so the cross of E and H will end up to the direction of K. And using this cyclical fashion, if you taking K first and cross E, it will tells you the direction of H. Now that I'm not putting equal marks here, we are only suggesting the direction of K cross E is pointing to the direction of H. And use this cyclical fashion again, we know that H cross K will be in the direction of E. So that's an important property with the three vectors that are orthogonal to each other, for the right-hand square principle. And this equation is what we use for finding the magnetic field intensity. So check out the formulation of this equation. We know that from the blackboard, the K is the direction of the wave propagation. And we know this direction for the wave propagating in the z greater to 0 region. Z greater to 0 region is in the positive z direction. So the first vector we put in here is AZ cross E, the electrical field, divided by eta sub 0. Why do we need to divide it by eta sub 0? Because the ratio of electrical and magnetic field is eta sub 0 in free space. So you need to take the eta sub 0 to get the correct number, correct magnitude for the magnetic field. So substitute AZ and the electrical field representation in the previous slides. You end up with this expression. Now that this is AZ cross AX or minus AX, AZ cross AX. So you end up with AY, okay. Okay. So the first term is in the AX direction. So AZ cross AX is AY, and AZ cross AY is minus AX. So the second terms comes with a minus sign, minus AX. Okay, and originally for the expression for electrical field, it comes with a magnitude of 10, and you need to divide it by 377. That is the intrinsic impedance of wave in free space. So you end up with this expression. Of course, here you can reorganize the order of the two terms. So you end up with this term in the x direction and this term in the y direction. So that's the calculation or derivation of the magnetic field using the representation of E field and the propagating knowledge about propagating direction. All right, the next example we like to look at is example 3.12. It talks the so-called antenna array. All right, antenna array is become more and more popular because we are moving into the region of millimeter wave, and also because we are nowadays the most popular topic in microwave engineering, I guess, is probably the LEO, Low Earth Orbit Satellite, 低轨卫星嘛， 所以在微波领域里头，目前比较热门的领域，大概算是那个低轨卫星的应用哈。那还有刚刚提到的毫米波的传播嘛哈。所以在这2个领域里头，因为距离远，然后波长频率高啊，即便在低轨卫星传统的那些 C band 啊、X band 已经还是有在用了，但是没那么的好用啊，因为说我刚刚提到了嘛，因为好用的低频频段已经大部分被占用了，所以新兴的应用啊会用在高频，那所以就催生了阵列天线的使用啊。那当然，我们这门课其实不是在讲天线了哈，当然天线算是微波领域在 free space propagation 里头最直接的应用，其实就是天线的设计了哈。所以我们昨天稍微提到一个阵列天线的概念。所谓的阵列天线，也就是说它不止一个它有多个单元天线所组成。那它主要能够提供的效能是它的波数可以集中，甚至透过各个单元天线的 excitation 的改变，特别是相位的改变，它可以让波数的方向切换，或者让波数的方向旋转。这个东西用在什么东西啊？我们讲一个最简单的，像是神盾舰，好吧？大家都听过神盾舰嘛？神盾舰跟传统军舰上面的转的天线差别在于什么？神盾舰的那个天线波数你看不到啊，但是各位上电磁学要发挥一下想象力嘛，哈，想象你能够看到那个神盾舰的那个波数的话，它其实是用电子的方式切换，意思是说它可以在 millisecond 的 order 就去切换天线，所以神盾舰之所以厉害，或者说它之所以昂贵，是因为它可以在同一个时间同时监控上百个目标物啊。但是你假如这种传统的转天线，它1秒钟最快也是1秒钟转1圈而已啊，所以它能够同时监控、同时追踪的目标物数量就是有限的啊。So in this example, we will talk a little bit about the principle of array antenna. So let's look at the case. Suppose that we have 2 infinite plane of current sheets. And the spacing, the distance between the current sheets is a quarter wavelength, lambda over 4, a quarter wavelength. And they both carry out current of equal amplitude. However, the phase of the 2 currents are different by 90 degrees, or another way to put it is pi over 2, half pi radian. So to express this situation mathematically, let's say JS1, the first current sheet, the magnitude is J sub S0, and the current at this moment, say T equal to 0, is flowing downward in the minus AX direction. And the function associated with this current source is cosine omega t. So you know the frequency. And you also know that it's a sinusoidal signal. And it's located at a z equal to 0 position. The other current source, which is placed right next to it, and in a parallel configuration, it's named as JS2. And it's located at the position of z equals to lambda over 4. So the spatial difference is about a quarter wavelength, 1/4个波长, quarter wavelength. And the excitation on the second current sheet is minus J sub S0 sine omega TAX. Okay, so you see, they are of the same frequency. The only difference is phase difference. The one is cosine omega t, the other is sine omega t. So we know that they have a 90-degree phase difference. And the sine omega t can be represented alternatively as cosine omega t minus pi over 2. So we know that there is a difference in phase for the two currents as pi over 2. All right, so we have two current sources. The two current source, the two current sheet, will produce electromagnetic wave. And a simple engineering technique is you can calculate or you can find out the expression for the field produced by the two sources independently or individually, then adding up the field together to get the total field. All right, so let's look at the field produced by the first current sheet. All right, so here as the remark says, 你先个别计算个别电流所产生的电场跟磁场，然后再把它们加总在一起。那只是在这个例子里头，在这个 example 里头，你看到的，你要注意到的是它的位置一个电流面是落在 z 等于0，另外一个电流面是落在 z 等于1/4个lambda。所以事实上，你要讨论的区域会被切分成3块 ，z 等于0。跟 z 等于 lambda over 4所以事实上，对于 z 等于0来讲，它的波是不是往这两个方向传播，往前跟往后嘛？那对于 z 等于lambda 来讲呢，它的波也是往前往后。可是从这一个箭头就可以看出来，我们事实上会把它看成是3个区域，对不对？这边是2个往负 z 方向传的波。这边是2个往正 z 方向传的波，那比较 tricky 的是在中间，中间是有一个往左，一个往右，所以我们看一下它这样所造成的效果会是怎样。Okay, so using the solution for infinite current source, we can write up the solution for the first current sheet as E1, the electrical field, which is in the form of current function, J sub 0 times cosine omega t minus beta z in the z greater than 0 region. And you know that here the argument is omega t plus beta z, so it's propagating in the minus z direction, right? And to the front is the magnitude of the two equations, which are the same for the two cases. Similarly, you can write up the solution for the other current source, that is J sub S2, which is originally in the form of minus J sub 0 S0 sine omega t AX, and we can write up its associated electrical field according to the similar function. So it's in the form of psi. Not that the position, because the second current sheet is centered at z equals to lambda over 4. So in the description of position z should have this offset. So here you see z minus lambda over 4 describes the center position of this current sheet. And so it appears in both regions, in the z greater than quarter wave length and z smaller than quarter wave length region. And here you notice that there is a difference in the sign. Minus beta and plus beta stands for components that propagate to the positive z direction and negative 1. All right, so we can reorganize this equation, this argument a little bit, because here we have lambda over 4 and beta is 2 pi over lambda, so they can be collected as pi over 2, all right? And pi over 2 can help you to transform this sinusoidal function the sine function into cosine function. So you need to check out this process. So at this step, because the existence of pi over 2 here, so the whole function transforms from sine to cosine, okay? And the other components that is propagating to the minus z direction can do the same transformation as well. So here you have cosine omega t plus beta z. Now that there's a negative sign in this region. And we can compare this result for E2 with the result for E1. Now that the region is a little bit, the description about the propagating region is a little bit different. Here is centered at z equals to 0, and this case is centered at z equals to quarter wavelength. All right, so the next things to add up, as the blackboard suggests, is to add up the corresponding components in the corresponding region. So we see for z greater than lambda over 4, you are actually acting this term with this term. So do you see any difference about the two terms? Well, they are exactly the same for region greater than lambda over 4. So in this case, for z greater than lambda over 4, the solution, the total field that accounts both E1 and E2 is this, beta sub 0 j sub 0 cosine omega t minus beta z, right? On the other hand, at a z smaller than 0 region, from this slide you see for z smaller than region, smaller than 0, you have eta sub 0 j sub 0 cosine omega t plus beta z. And for the second source, as long as z is smaller than lambda over 4, it's in the form of minus eta j over 2 cosine omega t plus beta z. So they are actually the same. They are nearly the same, except the sign are different. So the addition of the two in the z smaller than 0 region is what? Well, luckily it's 0. Okay. So as long as z is smaller than 0, the field, the total field is what? Is 0. So you have nothing. Now, in the other direction, you have double the magnitude of propagating wave for position greater than lambda over 4. And you have nothing for z smaller than 0, right? Okay. And the most interesting part about this solution is the region between 0 and lambda over 4. So for region between 0 and lambda 4, you are adding up this thing with this thing, the two terms. And you notice that one is in the form of cosine omega t minus beta z, and the other is in the form of cosine omega t plus beta z. So you have cosine alpha plus beta plus or minus cosine alpha plus beta. Okay, so use your high school trigonometry, you will end up with this expression, sine omega t times sine beta z. All right? So it still looks like a sinusoidal function, but the most critical part about this representation is what? The separation of parameter, the separation of argument, right? You see, in this case, in this region, the time domain description and the spatial domain description are separated into two functions. So you have sine omega t times sine beta z. So it can be no longer a traveling wave. It's not a legitimate propagating wave. It becomes the so-called standing wave. Okay, you know the field is non-zero in this region. The electrical field grows up and drops down. The magnetic field grows up and dwindles. Okay, from time to time. However, they cannot form a so-called propagating wave. Okay, I will try to show you some results graphically. Okay, you can determine whether or not it's the so-called standing wave or propagating wave. Okay, so we see The first region, z greater than quarter wavelengths, it's a propagating wave. The argument has both t and z description, so it's referred to as a traveling wave. 所以这边的 remark 告诉你，当 t 跟 z 是存在在同时存在同一个变数，在同一个function里头的话，它是有机会成为行进波 traveling wave 的表示形式。而在中间这个右边这个区域是 nothing 嘛 ，OK？ 你看不管时间怎么变，只要 z 小于0不管 z 的位置如何变化都是0所以那个地方没有波，没有 field， 那你就没有什么，没有能量所以你看看，透过2个无限大的电流源的设计，借由它们的空间位置的配置以及相位的控制你可以让波完全往正 z 方向传反过来你说我假如说把其中一个的比如说 J2 好了 ，J2 的相位从领先90度变成落后90度，那么它的能量会往哪边传？就会变成往负 z 方向传了，对不对？假如我是同相位嘞 ，J1 跟 J2 同相位嘞，你会发现什么事情？他们会一半的能量往前传，一半的能量往右传，干嘛呢？干嘛呢？不，他们的能量会变成一个往上，一个往下所以这类天线的好玩就在于说，你可以透过讯号大小以及讯号相位的配置，改变能量在空间中的分布。改变能量在空间中的分布。而在这一题里头，比较有趣的就是说，它在中间有一个区域是所谓的驻波 （standing wave） 因为在这个从数学式来看的话，它的空间描述跟时间描述是分开来的。OK， So here is the graphical representation shown in the textbook. So you can see that the solid line, the dashed line is the result of the first current source. I mean, the one placed in the z equal to 0. The what? Okay, the thin solid line, 细实线 is the result of the second source. And the blue line, the blue line and this both solid line is the result of the addition of the two field. So you see the magnitude in the positive z region greater than lambda over 4 is doubled. On the other hand, in this region, the blue line suggests the total field in this region is 0. And here is another case for t equals to pi over 4 omega. So it's about 90 degrees or something, right? So in this case, you see the field in the right-hand region is also still double. The total field in the left-hand region remain as 0. How about the total field in the middle between the two sources is the solid line? 我这边蓝线画的太多了画的太出头了其实那个蓝线应该要到这里就结束了，好不好？自己有 iPad 有 Pad 的自己调整一下这个蓝线应该只有到这里那他们的 total field 是这一个那这个的话是在下一个 time instant 的时候，它的 total field 会长成这样子然后所以这一个场型从天线的术语来讲叫做 n-phi direction， 往侧边排列的那个侧方向跑过去的那个辐射场型，我们叫 n-phi direction。那这边我给你看一个例子了，好了，我是用我们在做天线设计常用的一个工具，叫做 HFSS 来去模拟我们刚刚课本上所这个例子的情形我有一个偶极天线dipole antenna在这边，一个偶极天线dipole antenna在这边那当然它并不是无限大的电流面但它是一个有限大小尺寸的天线，然后我让它们两个天线的间距隔1/4个波长，就像那个题目一样。 然后呢，我去观察这2个天线在它邻近区域的能量的传播，它的场的传播的分布啊。所以，用这种我们叫做数值方法 （numerical EM tool） 啊，数值电磁方法啊，电磁数值方法，我们可以来去模拟天线它所产生的电磁波，所以目前大小的关系。那这个图呢，其实我做的事情只是把它们的那个相位做一个改变，把 antenna 2的相位从落后90度变成领先90度哈。那这个其实是跟课本上的描述比较接近、相同的啦哈，也就是右边的天线的相位领先左边的90度，所以它就变成往右传的，有没有啊？跟课本所看到的这个例子一样。那假如我们让它相位相同嘞，它事实上有往左右也有往上下了，往两边传，OK， 好，所以透过相位跟那个扩入大小的改变，我们可以操纵阵列天线在空间中的能量传播的方式、能量传播的分布 ，OK， 好，那我们再往下看。Okay, so let's move on to section 3.6. The title of this section is Polarization of Time-Varying Field. Polarization is 中文叫 polarization， 中文叫极化。好吧，讲点小故事好了。OK， 有没有看过那个立体影像？不过现在的同学应该都在物质充分的环境中成长哈，我们当然某种方式是幸运啦哈，但是有的时候就像跟老师比起来的话，可能有些小快乐、小幸福就没有体验到了哈。在我们小时候哈，就有所谓的3D 漫画，那个时候的3D 漫画是长什么样子嘛？那个漫画本子开起来的就是蓝色的线跟红色的线。你大概可以 imagine 哈，所以你要看那个3D 漫画的，就要戴上一个特制的3D 眼镜，然后一边是一个蓝色的玻璃纸，一边是红色的玻璃纸，好，所以蓝色的玻璃纸那边可以看到蓝色的线，然后右边红色的玻璃纸看到红色的线，哈。那当然你也知道，3D 成像的影像是利用什么视差嘛，眼睛的视差，所以你的那个漫画书上面的那个影像，一个你右眼看到右边该看的，左眼看到左边该看的，那你就看到立体的成像，那当然那种3D 效果非常的 cheap 但是在50年前40-50年前呢，也是很神奇啦，好不好？然后后来的话呢，就是最近好像刚好听到 YouTube 在看一个东西，叫什么六福村的那个消亡你们小时候毕业旅行有没有去过六福村？有哈 ，OK 哈 ，OK 哈。我可能是要算到高中吧我才有机会去六福村还有什么剑湖山对不对？还是什么的。好，那不管是剑湖山还是六福村，它一定有一个什么3D 电影院嘛，对不对？那3D 电影院的话，你要去看3D 影像，它还是给你发镜子，发眼镜嘛，对不对？那个时候看起来就比较高级一点了，为什么？因为那个眼镜看起来就是一个，也是一样白色的透明的塑胶片啦，对不对？那戴上去之后，你就可以看到立体影像。所以它用的方式是什么？它用的方式是 polarization， 也就是说，你那个时候的那个3D 影像的眼镜，它其实是2个线性极化的栅栏，在光学频段的线极化的滤波器也就是说，你戴那个眼镜，一边看到的是水平极化的光，另外一边看到的是垂直极化的光，所以投在荧幕上的话，会同时有水平极化跟垂直极化的影像那你用你的眼镜。所以这个叫做什么 ？polarization diversity 极化的分级啦刚刚我们讲的红蓝叫做 frequency frequency 频率多功频率双功frequency duplexing 那这边叫做 polarization duplexing。所以透过那个镜片，你就可以看到左眼看左眼该看的，右眼看右眼该看的嘛然后 可是那个东西就是说，你只要把那个眼镜反戴那你看到的就不是3D 影像了嘛，对不对？你只要把你的头靠到那个电影院，你坐你隔壁的人的那个头上转过去，你会看到你那个3D 影像也可能跑掉了因为它跟你的极化有关。所以后来有看过《阿凡达》嘛，对不对？是吗？是叫《阿凡达》吗？对 ，OK。阿凡达的时候，第一代的阿凡达的那个眼镜有没有看过？它是一个宽就多宽那事实上它上面有三个镜片一个是左眼，一个右眼，然后中间还有一个小窗户。那个时候是在做什么？那时候在做 time duplexing， 也就是说它里头是易经的，所以它萤幕上同时投影出左眼该看的跟右眼该看的只是说它的那个易经萤幕是在帮你遮眼睛，有一下遮左边，一下遮眼睛，所以在时间差上面去做分隔所以你讲他怎么样去控制说该遮左眼还是该遮右眼？就是透过那个中间那个小窗户，第3个窗户来去，因为萤幕前面还有一个红外线讯号红外线讯号告诉你去做同步跟你的眼镜去做同步，所以你把那个中间那个小窗户遮起来，那个3D 影像就不见了因为它没办法做同步。但是呢，我前半年就几个月前去看那个《阿凡达3》然后发现他们又用了一个新的版本那个新的那个眼镜上面找不到第3个窗户了所以他们大概，我猜他们应该是用 RF 讯号来去取代那个红外线的那个同步机制了OK 不过好吧，反正你要去产生立体影像的话，有不同的做法。OK, all right. So back to our lecture. The main topic is polarization. Okay, for naturally produced electromagnetic waves such as the sunlight, it has the sunlight in fact has polarization of arbitrary directions. Okay. And only man-made electromagnetic wave generation are of certain polarization. So, okay, all right. Let me try to write up the idea of this section in 3 minutes. Okay, so the polarization usually refers to the direction of the E field. So when it comes to polarization, we only talk about the direction of the E field. So, and as you already seen that how to produce an electrical field. Well, you can use alternating current. For example, here is the configuration of the so-called electrical dipole. 电偶极天线 dipole antenna. So on the dipole antenna, we try to provide current that goes up and down alternatively, and according to the Lenz's law, 冷次定律, you will have electrical field going to the opposite direction of the current. Okay. So what is the polarization of the electrical field for this vertically oriented dipole? Well, you will produce electrical field in vertical polarization. 因为你的电场跟它所产生这个电场的电流是平行的，所以垂直摆放的天线产生的是所谓的线性极化 （linear polarization）。However, linear polarization is in fact special case. For the more general case is the so-called elliptical polarization. That is, the direction of the E field will change its direction as it varies. It not only goes up and down, it also rotates. So this kind of polarization is referred to as elliptical polarization, 椭圆极化。And a special case for elliptical polarization is the so-called circular polarization, 圆极化。And a special case, another special case of elliptical polarization is linear polarization. 所以当那个椭圆，要么椭圆的那个长轴跟短轴一样大的时候，它就变圆极化。那只要长轴很大，短轴很小，短轴小到趋于零的时候，它叫做线性极化 （linear polarization） 所以讲到电磁波的极化，其实就是这三种 ：linear polarization、circular polarization 跟 elliptical polarization。那我们先休息5分钟然后我们再接下去讲极化相关的电磁波特性那个有其中